Good morning, everyone, and thank you. So I'm going to be talking today about our work on making tunable or remoldable inductors based on self-heating fusible alloys. So I'll begin by introducing the overall material set that we're working with. There was recently developed a family of smart composites based on a solid-liquid phase change. And what these are is a low melting point metal that's been embedded within a soft elastomer such as silicone or rubber. And so at low temperatures, when the metal is solid, you get the stiffness of the rigid metal, which is on the order of perhaps gigapascals, so a fairly stiff structure. If you heat it up, you can melt the metal, and now the elastomer begins to dominate the mechanical behavior. And so the advantage is that you can tune the elastic modulus from gigapascals to potentially hundreds of kilopascals, so many orders of magnitude change in the stiffness of the structure. So what we were interested in is trying to use this type of composite to create a reconfigurable system where we can dynamically remold or change the shape of an inductor. So at higher temperature, by heating it, you can deform it while it's soft, shape it into a desired form. Because the liquid metal traces freely stretch without damaging the structure. So one application of this would be something like if you had something wirelessly powering a sensor and you wanted it to conform to an unusual or non-planar planar surface. Once you've conformed it to the surface, you then cool down the device, and the phase change to a rigid solid locks it into position. So like other types of phase change actuation, one advantage is you do have a zero power latching mechanism that when it's fixed, it doesn't take power to hold that position. The trade-off is that because it's thermally actuated, you do have to use a fair amount of power during the remolding process. So this tends to be most suitable for situations where you're only remolding or only tuning occasionally. I now want to talk a little about what I mean by a fusible alloy. A fusible alloy is just a term for a metal that can be melted at low temperatures. There's a few different specifications for this, but one common one would be below 150 degrees Celsius. And these are a fairly common material set, mainly used for model casting and electrical solder. There are a number of different alloys. You can change the different ratio of different materials to tune the properties of the material. And I've listed a few of the more common ones here on the slide. The one that we've chosen to work with is a material known as Fields metal, which is an alloy of indium, tin, and bismuth. We're fond of it first because it's non-toxic, no lead, nothing so a fairly safe material to work with. And in terms of temperature range, it's meltable at only fairly modest power, so a melting point of only 60 degrees or 62 degrees Celsius, but it is high enough that it's unlikely to simply be exposed to that in the normal environment. And so we can only have it melt when we would want the material to be melting. To fabricate the inductors I'm working with, I use the technique known as microsolidics, where you fill fluidic channels with the metal in liquid form and then allow it to solidify to form the final structure. The fabrication process is shown here. I begin with just a 3D printed mold defining the inductor. I then fill it with silicone precursors, so liquid silicone, allow it to cure completely, then remove it from the mold. At this stage, you have open channels. I then seal it by bonding it to partially cured silicone, fill it on a hot plate with the material Fields metal, and then on the bottom left, you can see the actual finished inductors with the Fields metal, and they are fairly robust at this stage. Okay, the first application is actually trying to recast the shape. So I created a pneumatic chamber to pneumatically recast the shape of the inductor. So this is a chamber of high modulus silicone, a formulation known as Silgard 184. On the bottom piece of the inductor there, or the chamber there, and a cavity is defined in there to form the actual pneumatic chamber. There's then a 1 millimeter thick membrane of a soft silicone known as EcoFlex 30 that has an embedded Fields metal trace. And so before actuation, it's flat, just flush with the top of the surface. Then when I heat it by running a current through it and then apply a pneumatic pressure, it bends out of plane, and you can freely reshape it. You still get electrical contact. I can then cool it and then remove the pneumatic pressure, and it continues to hold the shape. If I then again apply current through it to melt it again, there's no longer the mechanical strength to hold it up like that. It sinks back to the initial position. So you can reset it to the original flat position. One application that we're aiming for in this is to actually make a tunable inductor using this mechanism. That the inductance of an inductor turns out to be very geometric dependent. That the self-inductance of the wires of the inductor changes based on the length and dimensions of the individual traces. The mutual inductance between neighboring wires changes based on the distance between the traces. So if we can physically deform the inductor, we can change the inductance. So you melt the traces, stretch it to change the geometry, and then solidify to lock it in place. So we have inductor tuning by mechanical stretching. We did some effort into modeling the behavior, and to quickly review some mechanical concepts. In general, in most materials, you stretch along one axis, you get compression in the remaining two. And the material property that defines this is known as the Poisson's ratio, the ratio between the applied strain and the counteracting strains. And in this context, because the metal, while you're stretching it, is liquid, the mechanical behavior is dominated by the surrounding silicone. And silicone, like most elastomers, is considered relatively incompressible for even moderate strains. This can alternatively be thought of as having a Poisson's ratio of 0.5, and so there is no volume change as we stretch it. This can also be written as saying that the mechanical stretches multiplied together must end up being equal to 1. Okay. Now to model how the inductor changes, this shows an equation for the inductance of a single planar coil, just a simple coil. And there's a lot of terms in it, but the really important one here is the average diameter, that it's linearly dependent on the average diameter. However, as I stretch it, I get effectively a different diameter along the x versus the y direction. So the way that we address this is to treat it as two different inductances, treating all of the channels aligned along the x direction as one inductance with half of the total, all the channels along the y as the y inductance. And because of this stretch relationship, that the stretches end up being 1, you can fairly easily calculate how the inductance will be changing, assuming that the diameter is just linearly varying with the inductance. Okay. So I created a mechanical testing setup for stretching the devices. This is basically just a 3D printed clamps designed to fit on a standard bench vise. And so I run current through it to heat it and melt it, and then use the vice grip or vice clamp to change the mechanical stretch. On the top right shows the inductor as fabricated. I then melted it and stretched it by 45%, and you can see that this is after it's been removed from the mold or from the clamp. It is holding its position. You can actually see the necking above and below the inductor, so the mechanical rigidity of the inductor is strong enough that it does hold it in its stretched position. I then can heat it again to return it to its initial state, again by just running current through. And the mechanical restoring forces of the silicone are enough to, again, bring it back to the initial as fabricated position. So we measured the inductance using an impedance analyzer in the original fabricated position, the stretch position, and the post-relaxation conditions. And first, it's somewhat reassuring that the inductance before and after relaxation are similar, that we haven't significantly changed the behavior before and after, or that it has restored its initial position. Also, as stretched, it's increased by about 50% in the stretched case. To conclude, this has primarily been an investigation of a technique for modifying an electrical device by melting and physically remolding the traces. So we're using a low melting point alloy embedded within a low stiffness silicone matrix. And the main applications here would be demonstrating for either changing or tuning an inductance or melting the inductor to conform to a nonlinear shape or surface. Now, even though we've chosen to focus on an inductor in this work, I do want to emphasize this is by no means limited to an inductor. You could definitely physically reshape other types of devices, something like a capacitor or a resistor, in a very similar way. That it is a fairly generic technique for remolding the structure. I want to acknowledge U.S. Army Research Labs for funding this under a postdoctoral fellowship, and I'd be happy to take any questions.